We have reached Chapter 4, where we will apply our solid theoretical understanding of X509 PKIs acquired in the previous chapters by using OpenSSL to construct from scratch a two-tier X509 PKI with an architecture as presented at the end of the previous lesson. This will give hands-on experience with various X509 PKI entities such as certificate authorities, certificate signing requests, and X509 certificates, and will allow to discover some of the intricacies around the trust provided by X509 PKIs with respect to the keys and ownership of the keys involved. The overall resulting X509 PKI we will then use in the next chapter to incrementally add security layers to the insecure emails exchanged between Alice and Bob in order to protect the emails from unauthorized access and to protect Alice and Bob from receiving spoofed emails. In what follows, the construction of the X509 PKI will proceed in some kind of a lockstep between a theoretical introduction to what is about to happen, which is then followed by a presentation on how the theory could be implemented with OpenSSL. This presentation on how to implement the PKI with OpenSSL will still exclusively be presented within this slide deck, but the presentation will, with full transparency, outline how OpenSSL needs to be used, and the presented commands are such that you can copy-paste these commands one-to-one into a Linux terminal in order to replicate this construction. The demonstration in the next chapter is then made with the PKI that was created by using exactly these commands as presented, and the reason I kept all of the presentation of this chapter within this slide deck is that in my opinion this allows for a much more concise presentation and discussion of the subject. Investigating the use and effect of the certificates on the security of emails is then, however, best presented with a real demonstration which will take place in the chapter following. Step 1 in the construction of the X509 PKI is the construction of the root CA. As a recap from the previous chapter and as a distinguishing feature, a root CA is a certificate authority with a public-private digital signature key that is not certified by any other certificate authority, but with the public-private digital signature key of the root CA being self-certified, which is also referred to as the root CA having a self-signed certificate. These root CAs are often the trust anchors of the X509 PKIs, from where the trust can be distributed across the whole PKI due to the transitive nature of the X509 PKI trust model. So in order to take part in a PKI, the end entities need to trust the root CA, which amounts to the end entities adding the self-signed certificate of the root CA to a so-called trust store of their systems and devices. As the trust anchor of a PKI, the private key of the root CA must be especially well protected, and real-world implementations of PKIs very often use hardware security modules HSMs, which are special-purpose hardware with highest security guarantees of keys residing within the HSM to never leave the hardware. The creation of a root CA key pair also needs to follow clearly defined protocols conducted by vetted operating personnel taking on clearly defined roles, with these protocols and the corresponding protocol logs then required to be presented to auditors in order to establish trust that the private key never left the room and devices it was created in. Once the root CA is created, it's then required to keep the activity around the private key of the root CA at a minimum, indicating that the root CA itself should be used at most to sign a small handful of CA certificates plus the regularly published certificate revocation lists if required by the policies of the PKI. So much for the theory. Let's finally proceed to creating our root CA. Our root CA will be a root CA with a 4096-bit public-private RSA digital signature key pair, and the lifetime of the public-private key pair will be set to 3,650 days, which is 10 years. Creating such a root CA with OpenSSL can essentially be done with one command, as presented on the left, which will result in two files, where the first file is the file containing the public-private key pair, which is indicated in blue, and with the second file being the self-signed certificate of the root CA. For this root CA, I specified the subject to have the name example.org root CA, which is a subject defined to live within the example.org organization and operating in Zurich, Switzerland. The meaning of the indicated key usage is a detail we will discuss on the following slide, but it's worth to observe that for the execution of this command, OpenSSL required me to provide a password, which is the password that OpenSSL will make use of to encrypt the blue file containing the private key of the root CA. This is again a detail we will get to see and discuss again in just a few slides. Once this command was executed, we are left with the blue file containing the public-private key and are also left with the yellow file, which is the self-signed certificate of the root CA. Let's first have a look at the self-signed certificate. Being on Linux, looking into files can easily be done by using the cat command. So using the cat command on the self-signed certificate then actually results in something that is not really humanly readable. With the first line and the last line reading begin certificate and end certificate, it's at least clear that the content of this file must be a certificate, but this is as far as it likely goes with understanding the content of this file. This self-signed certificate is of type Privacy Enhanced Mail, or PEM for short, and in this case the PEM file is a base 64 encoding of a binary version of the X509 certificate created, with this binary version actually being a distinguished encoding rule, DER, of the certificate structured according to the abstract syntax notation 1. This is quite a mouthful, and clearly this is not meant to be humanly readable. As the self-signed certificate of the root CA is not meant to be humanly readable, let's again just use OpenSSL to decode this self-signed certificate into a humanly readable format, which is something that OpenSSL can easily do via the command presented on this slide. With the help of OpenSSL, we then finally get to see the content of the root CA's self-signed certificate, and this self-signed certificate contains quite a lot of interesting information, much worth to talk through now. The self-signed certificate starts with an indication of the X509 version of the certificate, which for this certificate is 3, indicating that this certificate is a version 3 X509 certificate. The next field contained in the certificate is then the serial number of the certificate, which we can see to start with OB65 and so forth when expressed as a hex string. For this serial number, RFC 5280 defines this serial number to be a positive integer that can be freely assigned by the CA as long as the serial number is unique for each certificate issued by the given CA. The next field, labeled with 4, is the field indicating the signature algorithm used. The signature algorithm used here is the RSA-based digital signature algorithm making use of SHA-2 256 to hash the contents of the certificate to 256-bit hash values that are then encrypted with RSA to form the digital signature. Field 5 in the certificate then defines the issuer of the certificate. The issuer is defined via a distinguished name, which is composed of various attributes such as a country indicator, a state indicator, a location indicator, an organization indicator, and last, a common name. Here, the values I specified before can be recognized, and we can see that the certificate is for a root CA with name example.org root CA that lives in the example.org organization operating in Zurich, Switzerland. Next field up on the list is field 6 with the validity period of the certificate. I specified the root CA certificate to have a lifetime of 10 years, and this is now reflected with the validity period of the certificate starting from the 2nd of February 2022 and lasting to the 31st of January 10 years later in 2032. Just to be precise, the validity period indicates the maximum validity period of the certificate, as certificates can be revoked early by the issuing CA for reasons such as the private key of the subject leaked, a mistake being made by the CA during the identification of the subject, or due to the subject violating the terms of service and usage policies of the CA as defined in possibly also the certificate policy CP documents. Field number 7 then defines the subject of the certificate, which is again defined via a distinguished name, like the definition of the issuer in field 5. And here, for the first time, very interestingly, one can see that the subject defined in field 7 is the same as the issuer as defined in field 5, which indicates that this is a self-signed certificate with the root CA signing its own public-private RSA digital signature key pair. Field 8 then contains the public key of the subject together with information identifying the type of the public key. Here it's a 4096-bit RSA key pair, and the two values making up a public RSA key are a modulus and an exponent, both of which are listed, with the modulus being 4096 bits and starting with 00B3 when expressed as a hex string, and the exponent just set to 65,537, with this value being a very common and secure practice often implemented nowadays. Field 9 is then the field containing various X509 version 3 extension fields, which are simply just additional fields helping to narrow down the validity of the certificate. The first two extension fields list a SHA-1 hash of the subject public key and the issuer public key. These hash values allow for simplified identification of the public keys involved, which in the case of RSA really are keys of multiple thousand bits, and in this certificate right here, one can again see that the subject public key is the same as the issuer public key, again indicating that this is a self-signed certificate, as we already deducted by comparing the subject identifier field 7 and the issuer identifier field 5. The third extension field for the basic constraints then has one constraint reading CA true, indicating that this certificate is a certificate for a CA. If we look closely, we can see that the basic constraints are marked as critical, which indicates that everyone using this certificate must verify before each use of the certificate that the basic constraints listed are indeed true. Here, it would mean that each time the certificate is used, it must be verified that the subject delivering this certificate is indeed a CA. The fourth and last X509 version 3 extension field is then a field indicating the allowed usage of the listed public key. With this field, the public key of the root CA is defined to be used only for the signing of certificate and the signing of CRLs. These two use cases of the public key are very common for CAs and, for example, disallow the use of the public key for the encryption of data, which, if needed, would need to be done with a different key pair dedicated to that purpose. The last field of the certificate, field number 10, is then the field containing the digital signature created by the issuer of this certificate and across the content of the certificate, which are really just all the fields numbered 2 to 9. As this is a self-signed certificate, the digital signature presented and starting with 70DF when expressed as a hex string is the digital signature created by the root CA itself, making use of its own private key and with this certifying itself the binding of its public key to itself. This may sound somewhat odd, and in order to make sense, we must think back to the requirement that in an X509 PKI, one needs to have trust in the root CA in the accuracy of the certificates issued. If we have this trust, then what this digital signature proves is that the root CA indeed knows about the private key corresponding to the public key listed, which, in case the private key is properly safeguarded by the root CA, is impossible for anyone else to prove. This concludes the investigation of the self-signed root CA certificate, and I recommend you really to make sure to understand the purpose of each of these fields before going ahead into the next lesson. After having discussed in depth the first of the two files generated by OpenSSL for the root CA containing the self-signed certificate, it's time to look at the second file generated, which is the file containing the just freshly generated public-private key of the root CA. Simply displaying the content of the file with cat again makes clear that the content of this file with the public-private key of the root CA is not in a humanly readable state either, and this time the file with the heading and terminating line indicates that the content of this file is an encrypted private key. Again, this is actually a PEM file with a base 64 encoding of the binary distinguishable encoding rule applied to the abstract syntax notation 1 representation of the private key according to PKCS8 defined in RFC 5958. A PEM file itself doesn't provide any confidentiality, so OpenSSL encrypts the content of this file, which is why I had to provide a password to OpenSSL for the generation of the self-signed certificate. This password is then the password OpenSSL uses to encrypt the content of the file. Using OpenSSL to decrypt the key file can be done as indicated in the second command on the left side, and which makes clear that I again had to provide a password to OpenSSL in order for OpenSSL to decrypt the file. With this, the content of the key file then becomes accessible, and one can see that the key file is actually made up of multiple sections. At the beginning, the key file indicates that a 4096-bit RSA key is contained in it, and then starts with two sections that define the public key. As we know, the public key of an RSA key pair is just made up of a modulus and an exponent, which are listed in the field as the first two sections, and which we can recognize to be the exact same values as also being part and included in the self-signed certificate presented on the previous slide. The sections following the public key are then the sections listing the corresponding private key, which is made up of a private exponent and two 2048-bit prime numbers. Strictly speaking, the first three sections of the private key would be sufficient from a mathematical point of view for the decryption, but the last three sections of the private key are sections that help to speed up the decryption process, which is out of scope, however, for this course. At the core, the public-private key pair and the self-signed certificate is all that a root CA needs for its operation. Of course, a real-world implementation of a root CA would need to put in many security measures for the secure safeguarding of its private key, but the information presented is sufficient to understand the essentials of root CAs.